This is the inaugural meeting of the GIST Council. Apologies, I didn't start the recording right at the beginning.
So let's move into the disjoints part of this. Kind of an interesting talk I just put together on the airplane yesterday and last night. It's pretty good fun. I'm going to talk just a little bit about what disjoints are in OWL in general. I'm going to speculate a little bit as to why this is so underused and underappreciated, because we think it's an incredibly key part of ontology management. I'm going to go briefly through how disjoints helps you find logical errors, where it can go wrong, and what we've been doing with it. That's kind of the message for today. I mean, in a real brief sense, in OWL, when we say that two sets are disjoint, it means that they can logically have no members in common. It doesn't mean that they don't currently happen to have no members in common. It means that logically and philosophically they cannot have two members in common. So, and why sometimes we have to make this point, and why maybe, this is one of my theories, that disjoints aren't used very much in a lot of ontologies, is in a traditional system, there's this very implicit assumption that anything that's in a different table is of a different type and therefore isn't in the same set. You know, if you're making a very simple relational database, every time you create a new table, it's for a new kind of thing. So here we have the agent data table and the gadget table. And we don't worry about these being disjoint because they're just rows in different tables. There's nobody even sitting there thinking, well, you know, 007, the James Bond might be the same as the watch garrote, but actually it isn't. We know it isn't, and it's just kind of this built-in assumption, except when it isn't, because a lot of times, you know, after you get the first dozen or 2 dozen tables in your relational database, you start making these subtler and subtler distinctions where you put stuff in a table and you realize while there are different rows in these 2 tables, they might actually be referring to the same thing in the real world. And if James Bond, the patient, dies, then James Bond, the physician, is going to be dead too. But what ends up happening in a traditional system is there's something out of band that manages that, and it's not the system itself. So nobody thinks much about that. And the same with object-oriented. It's a little more nuanced. Any 2 instances, their subclasses of the same thing are assumed to be in the same set. So a checking account and saving account would be in the bank account, which isn't disjoint, but it's assumed that they're disjoint from each other. In other words, an instance of a checking account is not an instance of a savings account, unless you decide to invent a checking savings account that inherits from both, and then instances of that thing are in both sets. But the sort of behind the scenes assumption here is that every time you create a class, instances of that class are distinct from instances of any other class, and if you ever have to get them into another set, you end up casting them to the other class. So the net-net of all that, because there's nothing built into languages and nothing built into the design philosophies, it's just an exercise left for the developer, really. That somehow some developer has to know which of those tables, which of those sets can have overlapping members and which can't. But in semantics, we get much more explicit about that. Because in general, until we say anything else, any 2 classes or any 2 sets can overlap in any combination of ways. That the set of all mammals and the set of all ocean dwellers can, of course, logically have some members in common. They're simultaneously members of 2 sets. And in fact, we use this a lot in semantics. There's lots and lots of cases where instances are members of many sets simultaneously. Because that's the default assumption, it means we have to do something explicit if we want to say that that two sets can't overlap, that ET, the extraterrestrial, can't also be a mammal. Although in this picture it makes it look like it does, that's an invalid ontology there. And this gets even more interesting with inference, because we may have asserted that Flipper was an ocean dweller, and then may have had some properties in our ontology that allowed the ontology to infer that, in fact, Flipper was also a mammal. And if we didn't allow for the fact that those two sets could overlap, that we have pretty much immediately an inconsistent ontology there. So in semantics and protege, just kind of a reminder here, the way we declare disjointness, you go into a particular class. In this class, we have the class of all collections. And then down there in the lower right, we just say, what other set is that set disjoint with? In other words, a collection is not a person, a collection is not a magnitude, and a collection is not a unit of measure. You might think that it would be an easy thing to say these are all disjoint with each other, but we'll get into both why that's not as easy as it sounds and why that's maybe not the answer you want. Because pairwise, every set of sets, I guess every pair of sets, we need to evaluate differently. So there's one evaluation that say, can mammals overlap with ocean dwellers? And then we consider reptiles. Well, what we know about reptiles is that they're disjoint with mammals, but they're not necessarily disjoint with ocean dwellers. You have to go through pretty much every pair and say which set cannot overlap. As it turns out, luckily, subsumption, or having subclasses, is a nice shortcut, because once we know that no mammal can be a reptile and that person is a mammal, we already know, or the inference engine knows, that no person can be a reptile either. So here I clicked on the one of the things below collection, which is called ordered collection. As you can see, there's no disjointness asserted here, and yet a few slides ago we saw that collection was disjoint with three of the classes. But then after you run the reasoner, and as you do that, everything goes yellow. We see that nicely that the system has inferred that because ordered collection is a collection, then therefore it has inherited, essentially, or inferred that it's disjoint with those three things. Now, that's kind of what disjointness is. In a minute, I'm going to talk about what we use it for, because I think it's a lot more powerful than people give it credit for. But while I was putting this together, I went out and just had a quick look at some of the more popular ontologies that are out there, just to see what other people do. The Dublin Core, which is one of the popular ontologies out there, has no disjointness axioms in it. Not surprising, it has almost no classes. I looked at a client's infrastructure ontology, and it had one disjointness assertion, which is sort of interesting. SCOS had 2, FOF had 4, FIBO had 37. And all those small numbers are interesting. It suggests that the ontologists know what disjointness means, so they know how to put a disjointness axiom in, but I'm going to suggest they don't know how important it is and why it might be valuable to be a lot more comprehensive about what they're doing. And then I just happened to wander into the biontology portal, where I found a staggering 244,910 disjointness axioms. who knows? Maybe that's correct. So, and then I also did DBPD, but I wanted, this one was probably the most interesting of them all, because out of 754 classes, which is actually, they're starting to get down to reasonable, manageable size now, there's only 25 disjointness axioms, and as you can see here, they're sort of interestingly curious. Most of them are things that cannot be persons, and some of them are very high level. Activity cannot be a person. Okay, building, that's not bad. Escalator, I mean, why in the world do we need to, or maybe they inferred that one, but it's certainly kind of random. And then every once in a while we get dogs aren't cats. Yeah, but there's not a lot more things here. We've got the prehistoric period cannot be a historical period. That was a bit of a stretch, but religious organizations can't be spatial things. But you know, you can imagine there's a whole host of logical disjointness between 754 classes that aren't being stated here. And just by the way, if anybody who's curious, if you want to go find out, it's not very hard to find out how many disjointness axioms are in a given ontology. You just find their sparkle endpoint and write this query. And you just say where the subject is disjoint with the object, because they'll always be classes, then just count up the subject, and that's your count. That's how you find 244,910 disjointness axioms in the biontology portal. So then I asked myself, I scratched my head, why are there so few? One reason, looking at some of these ontologies, is most of them have, in the first place, too many classes, and DBPD, 750 classes. At their top level, I've forgotten now, but 80 or 90 classes that without any parent other than owl thing. And it's when you have that many numbers, it's hard to get your head around and get agreement on which things can or cannot have shared membership. Also, as the sheer number of classes increases and you run inference, when you try and export it, at least from Protege, it starts to warn you that at some point, because there's a combinational explosion here, it warns you that it could take a while. But I suspect a more compelling reason is that secretly many ontologists would rather be vague than precise, which sounds sort of odd, but they put classes out there and they put sort of generic descriptions on them, and hope that people can use it, and by putting any kind of constraint on it, you know, they're thinking that somebody won't use it. But our position is if they're not precise and two people use something that's vague and they use it inconsistently, it's just a matter of time until they create the problem, until they recognize the problem they've created. And you know, I think they don't want to, what I call, jar anyone, because as we'll see in a little bit in this presentation, if you do put disjoints on, that it doesn't take very long before somebody using the ontology is going to go, whoa, what was that? But really, I think if I were to sum all that up, I think most ontologists are just too wimpy. I think you really need to take a stand, and if you're going to take a stand, you can declare it in your disjointness, and then people at least know whether they should or shouldn't go along with that. So let's just go through a very simplistic example just to make sure we're on the same page. Here's what I'm talking about. I put together this very simple little ontology, a test ontology that had three little properties called lives in, works in, and occupant. And this is, I did this because it's kind of the classic way that you get things backwards when you're putting an ontology together. So in this case, we said lives in, the domain is person, so we meant anything that lives in something is a person. We could challenge that, but this is just this little demo here. And that any anything you live in is a house. And then we said, it sounded reasonable, that the inverse of that is an occupant. In other words, the house has an occupant. You'll notice this is right when you start to get on the slippery slope of naming and maybe suggesting, should this have been the other way around? So we went on the other side of it. I can't tell if people are arriving or leaving, but I'm hearing beeps, but looks like most everybody's still here. So I went in and created a definition of a person, and I said a person is equivalent to an occupant of some house. And that looked, you know, pretty innocuous. This is the kind of thing you do all day long in making up a definition. But then ran the reasoner, and the reasoner said, oh, well, therefore, that implies that a person is a house. And if we hit this little question mark button here in Protege and said, wow, that's kind of weird. I don't know very many people that are houses. How did you come to that conclusion? And the reason will tell you, well, people are occupants of some house. Lives in the inverse. Anybody, the domain of lives in is person, therefore the range of occupant is person. I think I got that backwards. But in any event, it ran its reason and came to this conclusion, which is clearly wrong. But my point is, if you didn't have any disjoints in your ontology, as this particular example does not, and if you had dozens or hundreds of classes and restrictions and all that kind of stuff, the odds of your noticing this are very slim. You know, there's a lot of desk checking and stuff to have found it. But instead, if you just, when we originally designed the class of person, said, you know, no person is a house, no house is a person. Those are two sets with no overlapping membership. Then when you run inference, I mean, you can't get past this. It's just right in your face. You have created two different classes that are logically subclasses of the class of owl nothing. These are classes that cannot have members. And if you, again, click the little question mark there, it will tell you exactly why they can't have any members in common. And if you had asserted people to be members of either of those classes, the ontology would be in even worse shape. Ontology would be inconsistent rather than unsatisfiable. It would just stop doing reasoning altogether. In this case, you can still do some reasoning, but we know from experience that once you start getting all this red ink all over your ontology, it's time to go back and figure out what you did. So that's kind of the general where it is, how it works sort of thing. There's a kind of a warning I want to give because of the way disjoint is kind of inherits down. If at a high level, in some upper level ontology, somebody said, you know, people can overlap with organizations. Some people make that argument from the Supreme Court and all that kind of stuff. And you either make this argument or you don't. You either say they're disjoint or they can overlap. In this case, we said they can overlap. And then imagine if somebody imported that ontology, didn't say much more about it, used some of those concepts, maybe specialized them, doesn't much matter. And then imagine a third person imported the ontology and then declared that person and organization are disjoint. This is a huge problem, mostly because anybody in any of the upper ontologies could easily and correctly have said that an instance can be, and maybe even is, a member simultaneously of person and organization, and now it's going to blow up. And you may discover this right off the bat, or you may not discover it for quite some time. But you've got a ticking time bomb kind of in your ontology there. So the implication for us is that we're declaring all of our disjoints at the highest level in GIST. It is okay in a few cases to make low-level things disjoint from each other, but any further down in the gist tree or anything derived from that, we shouldn't be making additional disjointness declarations about things that were defined as primitives. We're really focusing on the primitive concepts because pretty much everything now is derived one way or another from just a little bit more than a dozen primitive concepts. And once you know how they either can or cannot overlap, then all the rest of your ontology is pretty much safe. So here's how we thought about this up till now, up to the current version of GIST. We took on the left here and across the top the key high-level primitive concepts in GIST and just made sort of a little truth table there to say, just logically, or what we know about the world, should these classes be disjoint from each other? And we've had some discussions, and this isn't necessarily perfect. It seems like a reasonable starting point. It depends, obviously, on how you define some of these things. And that's the whole point. This is what this is all about. But and this is very experimental and early right now. I'm doing a refactoring of GIST, and mostly, well, in fact, mostly not changing what anything means, but changing flattening out the import hierarchy. But I decided to also tackle this disjointness issue one more time while I was at it. I realized it was a little bit hard to read, but in this circle, I put some really primitive classes that are mostly mutually disjoint with each other. That's why there's such a web of lines here. But there's a few, and I put them near each other in the clock here, like time instant and time interval, or georegion or geopoint, where you can make a pretty good argument that to not make them disjoint from each other. You can see the little bits of white space there. And then there's a few other primitive concepts that are around a little bit further out from the central circle, and I put them near things that are analogous to. I'm still working through, and I'm going to work with Michael and Andy initially to figure out exactly what we want those declarations to be. I should have mentioned at the very top level of GIST, there's, or maybe that's not quite the top level, 52 classes of 64 disjoints derived from this table. So far, just from the top 36 classes, this seems a little bit high to me, but with 384 different disjointness assertions. But I'm very optimistic that they're going to be both light and useful. They're useful in finding. The first place they're useful for is finding errors. The second place is we've built some dynamic user interfaces, and one of the things we want to do is anytime somebody is building a form or building something, we want to prevent them from putting together things that would be illogical, which pretty much is the disjoints. So, summary of what's going on with disjointness and GIST. We think not only is it a powerful way to catch logic error, it's really just about the only way. Every time we've looked at errors that we have induced in the act of building an ontology, if you go back and take out the disjointness assertions, you won't see the errors. So it kind of brings logical errors to the surface there. And our observation of a lot of other ontologies, they have so few disjoints that they're very unlikely that you catch any logical errors, because that's your main weapon there. So we've got in GIST a small number of high-level concepts that are almost completely mutually disjoint, inheriting down to all the derived ones, and we think that's going to help both us and anything derived from GIST have a much better chance of catching logical errors. So that was it for